Welcome to Section 4 of Level 3 Aqueous Systems. And Section 4, I may have mentioned in my previous video that I like to refer to Section 4 as buffers and titration curves. And there's going to be two parts to Section 4. The first part is all about buffers, and we just spent a week teaching this stuff. And then the second part will be relating that buffer concept into titration curves. So just the layout for this video, I'm going to first of all define what a buffer is, and I'll try to use the blood as a natural example of that. We're going to look at the composition of an effective buffer. Number 3, 2 ways to make a buffer system. Number 4, illustrating how a buffer system works, which is basically writing equations. And number 5 then, as an asterisk beside it, because this is the main thing that comes up in exam papers, which is to calculate the pH of a buffer system. So if we just start off with section 1, which is what is a buffer. If you think about the blood maintains a pH of around 7 to 7.4, despite the fact that it has molecules constantly entering it from the food that we eat and molecules exiting it, which are needed by cells. For example, glucose is absorbed for respiration. So there's constantly molecules going in and out of the blood. And the question would be, well, how does the blood maintain a pH of approximately 7 to 7.4. How is that possible? And we need to introduce the definition of a buffer now. So the definition of a buffer, and I'll just use a different color for this. So a buffer will maintain a certain pH despite the addition. So we'll maintain a certain pH despite the addition of small amounts of a strong acid. And I'm just going to abbreviate all these now. So strong acid will be abbreviated to SA, or a strong base, SB. So buffer maintains a certain pH despite the addition of small amounts of a strong acid or a strong base. So in the blood there must be some molecule or buffer system which can maintain this pH of 7 to 7.4, and we'll come back to that when we talk about the illustrating. So we'll do this in section 4, illustrating how a buffer system works. But by definition, a buffer maintains a certain pH despite the addition of small amounts of a strong acid or a strong base. Composition of an effective buffer. So how do you make a buffer? So composition. Composition of a buffer. Basically, you can have a weak acid, so I'll abbreviate that to WA, weak acid plus its conjugate base. The key point here is that you want to have as close to equal amounts as possible, so you want to have a 1:1 relationship, mole relationship between your weak acid and your conjugate base. You could also have a weak base, WB, and its conjugate acid. Again, you want to have as close to equal amounts as possible. So good examples of each of these. A weak acid, you'll see it come up time and time again. Organic acids are weak acids. So ethanoic acid will dissociate in water and form its conjugate base, which is CH3COO minus ethanoate plus your H3O plus. But the problem with this situation is that weak acids only partially dissociate, as you may remember. So because they only partially dissociate, you must supplement the conjugate base, must be supplemented externally. So what I mean here is you need to, in order to make this an effective buffering system so that you have equal amounts of the weak acid and its conjugate base, you must externally top up the levels of the conjugate base. And that can be done by add some solid salt. So the salt of ethanoate would be sodium ethanoate, CH3COONA. So either in a solid form or as a solution. So as a solid or as a solution. And that's how you make sure that you have equal amounts of the weak acid and its conjugate base. A good example for a weak base buffer system. So weak base buffer system the weak base, ammonia would be a good example. It will naturally dissociate with water, partially dissociate and form its conjugate acid, ammonium, plus hydroxide ions. Again, though, because this is only partial dissociation, the concentration of the weak base is much greater than the concentration of the weak acid. To top this up, you can add some solid ammonium chloride, or alternatively as a solution. So that's what the exam questions tend to get at, is how much of the conjugate base or conjugate acid needs to be added in order to get the pH of the buffer system that you require. So we'll come back to those questions later on in the video. So that's the composition. So we've done what is a buffer. We've looked at the composition of an effective buffer. Two ways to make the system. I was just alluding to it right there. So part 3, just how to make a buffer system. Making a buffer system. So 2 ways. The first way is just like I've been talking about. Number 1, you add the salt of the conjugate base to a weak acid system. Okay, so example, sodium ethanoate being added into ethanoic acid. So it's literally taking some ethanoic acid in a beaker of a fixed concentration, and then you add a certain amount in grams of your salt in order to get the desired pH. You have a pH meter stuck in there just to keep track of your addition. Of course, vice versa situation, you could be adding ammonium chloride, like we just mentioned, into ammonia. That would be a weak base buffer system. And as I also mentioned, instead of adding it in the solid format, you could alternatively add it as a solution. So you could add it as a solution as well. And we'll talk about something to be aware of, which is a dilution factor. We'll talk about that when we're looking at our calculations. The second way, which is to make a buffer system, we just get a new page now. So the second way to make a buffer system, so we're still talking about making buffers here. The second way is, for example, to take a strong base plus a weak acid, okay, or alternatively a strong acid plus a weak base. And what you want to do here is you want to go to half neutralization. Half neutralization point will mean that you have equal concentrations of your weak acid and your conjugate base, or your weak base and your conjugate acid. So just a correction there. So this was supposed to be a weak acid and conjugate base. Conjugate base. And this was supposed to be weak base and conjugate acid. So if you just titrate a weak acid with a strong base as far as half neutralization, then you have this situation, and this is a buffer system. Remember, the definition said that we needed to have approximately equal concentrations of the weak acid and its conjugate base, or vice versa, the weak base and its conjugate acid. This is a buffering system. So for example, if you take ethanoic acid and you add some sodium hydroxide to it, the sodium hydroxide at half neutralization will produce sodium ethanoate, which will dissolve in your water, plus H2O. And when you get equal concentration, so at half, so at midpoint, also known as the half equivalence, also known as the buffer zone, buffer zone, okay, of a titration curve. So that's a nice link into titration curves for next week. This system will also have buffering capabilities because you have equal amounts of the weak acid and its conjugate base. There was also a question on an exam paper I was looking at just today, where they took a weak base plus a strong acid, And what they were looking at here was the formation of the conjugate acid for ammonia in that case, plus Cl minus. And in this case, again, if you go to the half equivalence, or the midpoint, then you would have had equal concentrations of the weak base and its conjugate acid, and therefore you have a buffer system. So just be aware of that. It might look a bit strange in an exam question if we're talking about adding a strong acid to a weak base and then referring to buffers, but what they're getting at is basically the second way to make a buffer system. So just to go back to the first page and keep a check on what we're covering, we've done what is a buffer. So it's a system with even amounts of weak acid in its conjugate base, or for the base system as well, which could withstand small additions of a strong acid or a strong base. We've looked at the composition of an effective buffer. We've looked at the two ways to make a buffer system, illustrating how a buffer system works. Okay, let's take a look at that now. So we're going to write some equations for this. All right, so illustrating how a buffer system works. These systems work is the question we're asking here. So if we take some examples, I'll do 3 examples. The first one I will do is a weak acid buffer system. Then I'll do a weak base buffer system. And then I'll do a nice context. I'll do example number 3, buffering in the blood, as a context for you. So a weak acid buffer system, if we take our ethanoic acid example again, so the weak acid, the conjugate base is going to be ethanoate, so that's the conjugate base. So this will deal with the addition of strong base from a strong base, and the conjugate base will deal with hydronium ions from a strong acid. So the equation will be as follows: ethanoic acid plus hydroxide ions will form the ethanoate, an extra O there. Whoa, get rid of that. So yes, the weak acid will react with the strong base and form the ethanoate, plus you get water. So this is a neutralization. So no effect on the pH. You'll also get a complete arrow because we're dealing with a strong base. And then the opposite scenario, or the other half of the system, the ethanoate, can deal with the addition of small amounts of a strong acid, arrow, and it will form ethanoic acid plus water again, so that's neutralization. So everybody's happy, the system maintains its pH. A weak base buffer system, if we take our ammonia as our weak base, and then the ammonium ion as our weak acid, this one will deal with the H3O plus from a strong acid, and this one will deal with the OH minus from a strong base, as follows. So ammonia plus H3O plus will form NH4 plus H2O, which is neutral, and the ammonium will similarly deal with any strong base, hydroxide ions, forming ammonia plus H2O as well, which is also neutralization. System is happy. Now let's just take an example of this in the blood. Now the blood needs to maintain a pH of approximately 7 to 7.4, which is neutral pH, predominantly water in nature. If you go above or below that pH, it can lead to death. So not a good situation. And we've just said at the beginning in the introduction, there are various molecules being introduced into the blood from the food that you eat and other processes, and then various molecules coming out of the blood. So there's constant need to keep buffering that system. So what we have here is, we're talking about carbonic acid or bicarbonate, H2CO3. Right, this stuff, what this molecule has the ability to do, strong base. I'll talk about that in a second. How does the carbonic acid form? Well, it's based on a reaction between the CO2, which is already in your blood from respiration, and then the CO2 from respiration reacts with the water, which is also in your blood, and then you form H2CO3. So that's the origin of carbonic acid. So this stuff is forming in your blood, and then the job of carbonic acid, I'll just highlight it in red so that it's associated with blood. Now, so let's write two equations to show how it deals with the addition of a strong base or a strong acid. Okay, so carbonic acid, like any acid, weak acid will undergo its dissociation in water, and it dissociates in water and forms either HCO3, which is the carbonate, so that would be the hydrogen carbonate ion, or alternatively you're going to have H2CO3, and from either of those species, CO3, the hydrogen carbonate will reform the acid, bicarbonate, or carbonic acid plus water, so that keeps the system neutral. Or alternatively, if a strong base is added, then the acid aspect of the system kicks in, and you form the hydrogen carbonate ion plus H2O. Both cases, it's kept neutral, and the person gets to live, which is good news. Obviously, if you directly injected a strong acid into your bloodstream, then that would not be a good situation. So again, pharmaceutics have a lot to deal with when they're developing drugs for injection. Okay, let's return to our list of things to cover. So we've illustrated how a buffer system works by neutralizing the addition of that strong acid or that strong base. And now we need to just focus on the real stuff which comes up in exam questions, which is how to calculate the pH of a buffer system. So I'm going to just do 3 particular examples, maybe 4, just to try and cover the range of questions that you'll come across. So we get a new page for this, and this is calculating the pH of a buffer system. Okay, so the last part of our video on buffers is to look at calculating the pH of a buffer. There are maybe 3, if not 4, major types of questions you can get on calculations. The first one is if you're going to add the salt to a weak base to make up a weak base buffer system. This question is taken from one of the exam papers. I can't remember what year, but it's there in front of you. You need to calculate the mass of solid ammonium chloride that must be added to 1 litre of 0.1 mole per litre ammonia to make a buffer of pH 9.4. You're given the molar mass of ammonium chloride, and you're given the Ka, the acid dissociation constant for ammonium. Now there are 2 ways to approach doing these questions, so I'm going to do it both ways just to illustrate it this one time. You can use either a rearrangement of the Ka expression. So we'll do the Ka expression over here, using the Ka expression. Or alternatively, you can use what's known as the Henderson, let's just spell these guys' names correctly, Henderson-Hasselbalch, so H-A-S-S-E-L-B-A-L-C-H, the Henderson-Hasselbalch equation. All right, and the Henderson-Hasselbalch equation is this: the pH of a buffer can be determined if you know the pKa, and then it's equal to plus log to the base 10 of the concentration of the base species, whatever it may be, over the acid species. And just make sure you put the right one on top and the right one on the bottom when you're doing that calculation. So 2 ways to do this question: using and rearrange the Ka expression if it's a weak acid. If this was a weak base Kb value you were given, you can convert that to Ka, or alternatively the Henderson-Hasselbalch equation. So let's take a look at what we have here. So what we're doing is we're making a weak base buffer system. We're taking a certain mass of chloride. We don't know how many grams to add to our ammonia in order to get the pH which is desired of 9.4. The ammonia concentration we do know to start with is 0.1 moles per litre, so we have that much. So the Ka expression for this system, it has to refer to the dissociation of ammonium because that's what the Ka value is that we're given. So the equation we're going to write is ammonium dissociating in water to form ammonia plus H3O plus. Now what we're doing here is we're trying to top up this content, we're trying to top that up by addition. So how many grams of ammonium chloride do we need to add? That's the question we're asking here. Alright, so we write our Ka expression for this. Our Ka expression is equal to the concentration of NH3 times the concentration of H3O plus over the concentration of your ammonium. Now, if you guys remember from when we were doing the dissociation of a weak acid before, we used some assumptions and said that the concentration of your ammonia and your hydronium ions must be equal. In this case, we can't make that assumption, and anyway, we're not interested in the pH at the moment. We are interested in the concentration of NH4 plus. So there's no need to isolate H3O plus in this case. We're interested in the concentration of NH4 plus. So you want to rearrange your Ka expression and isolate NH4 plus on its own, and we do that, we end up with this expression. Concentration of NH4 plus is going to be equal to the concentration of ammonia times the concentration of H3O plus over the concentration of, over the, not the concentration of, the Ka value, excuse me. Back to my pen. The Ka value which you're given. So do we have all these entities? Well, if we look back to our question at the start, the concentration of ammonia, if we look back into the question, concentration of ammonia was given as 0.1 mole per liter. The pH will tell us the concentration of H3O plus because 10 to the negative pH will give us the concentration of H3O plus, which works out to be 3.98 by 10 to the minus 3 moles per liter. So we have our H3O plus, we have our ammonia, and we have our Ka value right there. So our calculation is going to be as follows. The concentration of ammonia equals, the concentration of ammonium equals 0.1 moles per liter times the H3O plus, which was 3.98 by 10 to the minus 10 moles per liter, over the Ka value, which was 5.75 by 10 to the minus 10 unitless, and this works out to be a value of 0.0692 moles per liter for our ammonium. Now that there is the concentration, so we have the concentration now of ammonium, and our question originally said what mass of ammonium, so we're not quite there yet. To get concentration into moles, we need to use two triangles now. Alright, we got concentration equals moles over volume, and then we have, it's a little bit small, I'll make it bigger. We also have time molar mass. So what you're trying to do is you're trying to get from here to here. So moles from the first situation, the moles will be the concentration times the volume, which will be 0.0692 moles per liter. The volume that we're given here is a liter. If we look back to the question, it was just sneakily thrown in there that you have 1 liter, so the volume is easy to consider here. That just simply means multiply by 1 liter, so our moles equals 0.692 moles. And the final step then, mass is going to be equal to moles times molar mass, which is going to be equal to 0.0692 moles by the molar mass, which you were given in the question as 53.3 grams per mole, which equals to a final mass of 3.7. Now that should be the 3 significant figures. So slight correction there. If it's the 3 significant figures, then it's 3.69 grams. Okay, so that's one way to do this. Now, it's much quicker, you'll find, to use the Henderson-Hasselbalch approach. The pH for the buffer, you already know you want it to be 9.4, so that's what that is there. The pKa you can determine from the Ka, because remember the pKa is just log to the base 10 of the Ka. So that works out to be, so the pKa works out to be 9.24. And we just need to isolate the species that we're interested in. We're interested in the concentration of the acid species in this case. Okay, so we're interested in the concentration of the NH4 plus. What is that? So the log to the base of the base, concentration of the base species over the acid species. Now the base species, I should also add its concentration because we know it too. Concentration of our base species, again in the equation, was 0.1 mole per liter. So we can put that in there in the expression. And now the expression looks a little bit unmanageable still because we have log to the base 10 of everything here. So we need to change things around a little bit, bearing in mind that we're focusing on the concentration of the acid. So what we're going to do here is we're going to take this across. If you subtract them, it becomes 0.160 is equal to log to the base 10 of your 0.1 moles per liter over your concentration of NH4 plus. To get rid of the log 10, you just inverse log 10 on your calculator. So just shift and then log 10 on your calculator, and that will sort out the log 10, and then you need to do the same on the other side. This number becomes, okay, so if you get the inverse log of both sides, the 0.160 becomes 1.45, and then this becomes just 0.1 moles per liter over the concentration of NH4 plus. With a little bit of manipulation, this will become, concentration of NH4 plus is going to be equal to 0.1 divided by 1.45, which comes out to be 0.0691 moles per liter, slightly off the 0.692 that we got using the other method, just because of slight difference in the way we're doing the calculation. We need to finish this out though. You finish it out the exact same way, then you take a 0.0691, put it through this process, and you should come out with a mass which is pretty much the same as 3.69 grams. So there's no need to go through that again in the video. So that's the two ways to approach doing that question, and in both cases you're looking for the mass of salt to be added. An alternative type of question to look at is if you have to top up the salt using a solution, and a dilution factor needs to be considered. So I'm just going to do this as my last example because I'm eating into way too much time here explaining these. So one more example, and then of course you can check these answers yourself in exam papers. I'm going to write out the question first. Alright, so the final question I'm going to do on calculating the pH of a buffer is this situation where you're supplementing the conjugate acid or conjugate base species by adding a solution of the salt. So what we have here is, in our particular question we're doing now, I'll just use black for this, we have a buffer solution was made by mixing 200 mils of ethanoic acid with 150 mils of sodium ethanoate. So you have your ethanoic acid already in here, 200 mils of that, and the CH3COOH aqueous. And to that you're adding from a little container the solution for its salt, which is sodium ethanoate, CH3COONA, and this is also aqueous. So you're dropping that in there. You're adding 150 mils. So when you're adding two solutions together, you must consider the dilution factor. So dilution factor, which affects the concentrations. So if you don't do that, then you get the wrong answer. So the first thing we need to do here is we need to assess the concentrations that we have for the weak acid and the conjugate base. The weak acid's initial concentration is 0.10 moles per liter, and the starting concentration for your sodium ethanoate solution is 0.15 moles per liter. With the dilution factor, the concentration of CH3COOH is equal to its zero point 0.1 moles per liter at the original, and multiplied by the dilution factor. So what we had was 200 mils of acid, then had 150 mils added to it to give a total volume at the end of 350 mLs total. So the dilution factor is 200 over 350, and if you multiply that by the original concentration, the diluted concentration becomes 0.057 moles per liter. Alright, so that's the diluted concentration of the acid. And then similarly, we must consider the conjugate base, and its original concentration was 0.15 moles per liter. Again, the dilution factor here was we took 150 of the conjugate base and put it into a total volume of 350, which gives you a diluted concentration of 0.064 moles per liter. Now we've got the right numbers to use, and the second part of this question is to work out the pH. What's the pH of this buffer system going to be? And we can use either of two ways. We can use the Henderson-Hasselbalch approach. I'm just going to use the Ka expression this time just to show the equations of what's happening. So in this situation, dissociation, we're given the Ka value for the dissociation of ethanoic acid. So that is the equation that we need to write. We've written this many times now at this stage. So partial dissociation in water plus H3O plus. And of course, the reason we're adding the solution is to supplement that concentration with the addition. So that's supplemented with this addition right here, so that we get equal concentrations of both of them. The Ka expression is going to be the ethanoate times the H3O plus over the concentration. In this case, we're interested in the pH. So we're interested in the concentration of H3O plus in this case, so that's the one that we want to isolate. So Ka times the concentration of ethanoic acid, which was diluted, over the concentration of the ethanoate, which was also diluted, will give us the concentration of H3O plus. So the numbers we want here, that's going to be 0.064 moles per liter. This is going to be 0.057 moles per liter, and the Ka value is, in the original question, 1.75 by 10 to the minus 5. That gives you a concentration of H3O plus. So the concentration of 1.56 by 10 to the minus 5 moles per liter, and then the pH of the buffer is equal to log the base 10 of that, which works out to be, let's just do that now, here, so which works out to be 4.8. So those two questions are quite involved and show most of the aspects of the calculations that you have to do for buffer systems. I could have done an example of working out the pH of a weak acid buffer system, but that's been included in this second example. So remember, you can use the Henderson-Hasselbalch for all of these types of questions too, and you should do both ways if you've got time in your test, just to confirm that you have the right answer. The next topic is going to be titration curves, and that will be 1 week's teaching. And there's 3 types of curves we want to look at, and buffers have a little part to play, like we said, at that midpoint when you have equal amounts of the conjugate acid and the conjugate base.